All right, so let's work our way through 7.27. This is another one of these pathways problems, okay? This problem extends upon 7.23 that is presented in an earlier video. Um, and basically, this is the work from 7.23. If you've already watched that, it's going to be helpful. But basically, what 7.27 asks us is to calculate the energy difference, delta E, for a mole of hydrogen atoms undergoing the n equals 5 to n equals 2 transition that we considered in the earlier problem. So in the earlier problem, just to recap, okay, we considered a transition in hydrogen from a higher to a lower level, 5 to 2 for the Bohr orbits, okay? And we can, of course, use this Rydberg equation to figure out what the wavelength of light that's associated with that transition is. And what we ultimately found was that that wavelength corresponds to 434.17 nanometers. Okay, that's the wavelength of light that we expect the hydrogen atom to emit when it undergoes this 5 to 2 transition. Now, what this problem does is it extends upon this idea to calculate the energy difference for a mole of hydrogen atoms. Okay, we wanted to tackle this problem for a couple reasons. One, it doesn't talk about wavelength anymore. The other problem talked about wavelength, 723. But this one also uses wording and terminology in the problem that I think we want to be a little bit careful with, and we want to carefully consider when we're answering the problem. Okay, just so we're all on the same page, we really understand what we're talking about and what we're doing. Okay, so if we want to calculate an energy that's associated with this process, it stands to reason to me that we ultimately want to refer back to this E is equal to h nu business, because that always gives us the energy of a photon. Now, in this case, we have the wavelength, not the frequency, so we have a little bit of work to do. We need to use this equation, which tells us that the speed of light, 2.99 times 10 to the 8th meters per second, is equal to the wavelength of a photon times its frequency. Now we want to solve for the frequency so we can plug it into that equation. What do we know about the wavelength? Well, it's 434.17 nanometers. I've got to convert to meters here by multiplying by 10 to the minus 9. Okay, now that's going to be in meters units because this is in meters units. I can then very quickly rearrange and solve this particular equation for my frequency, which is 6.8867 times 10 to the 14th. Okay, so the frequency of this light is 6.8867 times 10 to the 14th hertz, if I've done all my math correct. Now, of course, the beauty of this is I can plug that number into this equation. H, of course, is my Planck's constant, 6.62 times 10 to the minus 34 joules second. And I multiply that by my frequency, 6.8867 times 10 to the 14th per second. This is a 4. Okay, second units cancel. And I am left with an energy in joules, and that energy is 4.55897 times 10 to the minus 19 joules. Okay? Now that we've used these equations for this n equals 5 to n equals 2 transition in hydrogen, I feel like we need to take a second to remind ourselves what these numbers mean. Okay? The wavelength is the wavelength of light that we would expect to get from this transition, from a hydrogen atom, n equals 5 to n equals 2 transition. The frequency, number of cycles per second of the wave that corresponds to this wavelength. This frequency gives us this energy. Now that energy is a single photon of light of this frequency, of this wavelength. That energy would originate from a singular atom emission. from the 5 to 2 level. So this energy, we could call that a delta E. That is the energy gap between the n equals 5 and the n equals 2 level in the hydrogen atom. That delta E is 4.55897 times 10 to the minus 19th joules. That's what it corresponds to. That's the difference in energy between these levels. And that energy difference manifests itself as a photon of this wavelength. Okay? That's what we've calculated. That's for one photon. And this corresponds to the energy gap in the hydrogen atom. Okay? For any given hydrogen atom. It doesn't matter how many we have, they're all the same in this sense. Okay? Each of them have this energy gap. So the problem in your book starts talking about compute the energy gap delta E for 1 mole of hydrogen atoms. And I read that, and I wanted to take a few minutes to kind of go through this and explain, because all of the atoms, if you're talking about the n equals 5 to n equals 2 level, they all have this energy gap. They're the same. Okay? It doesn't matter if you've got 1 or a mole. Now, will the number of photons which are emitted by a collection of atoms be different depending if you've got 1 atom or a mole of atoms? Yes, because if you have more atoms, obviously you have the opportunity for more photons to be emitted, but they're all going to be this wavelength because this energy gap is the same in every hydrogen atom that created all of the photons. Okay, you just have a larger quantity of photons that are the same. It's 434.17 nanometers. So I didn't like the terminology of your book saying calculate delta E for a mole of photons. The delta E depends upon what we're talking about. We're talking about a hydrogen atom here. That energy gap between the levels is always the same for every hydrogen atom. It's always this if we're talking about the 5 to 2 gap. But what we can do maybe is compute the total energy for 1 mole of photons emitted for the 5 to 2 transition. Okay, so the wording is a little bit different here. If I asked you to compute the total energy for a mole of photons for the 5 to 2 transition in hydrogen, well, I can do that, right? Because each one, so this number is for 1 photon, the total energy is just the sum of all of them. So 1 has an energy of 4.55897 times 10 to the minus 19th joules. That's just for 1 photon, right? Because that's what that equation does for us. If I want to compute the energy of a mole of them, I need to multiply by Avogadro's number, 6.023 times 10 to the 23rd. So I'm just scaling up to a mole instead of having 1. Now I've got a mole. Okay, so for a mole of hydrogen atoms, you end up doing the math. You get 2.745. So 2.74586, if you want some more sig figs, times 10 to the 5th joules. This is the energy of 1 mole of photons that are produced from the n equals 5 to n equals 2 transition in hydrogen. All I did is I add up the energy of all the photons that make up a mole of photons. That would result from maybe a mole of hydrogen atoms, okay? But the energy gap in hydrogen is always this. It doesn't matter how many hydrogen atoms I've got, that the gap between the energy levels is 4.5589 times 10 to the minus 19 joules. It's just the way hydrogen's built, constructed. So I wanted to work this problem again to go through the differences in language and terminology and really get you to focus on the importance of that so that you know what you're calculating. That's really kind of important. Know what you're calculating.